I just wanted to make a few short announcements. Our next speaker is Rick Sakeley, who's a professor of chemistry here at Berkeley, and he's going to be speaking on what makes water wet, and that's on May 8th. And if you would like to get a reminder about 1 week prior to the lecture, I'm going to send around this sign-up sheet. I know a lot of you are already on the email reflector, so you don't need to sign this if you're already getting reminders. And does anyone have a pen that they could, that they could send around with this? And I just wanted to say also that the first lecture was Art Littleworth, and he is a famous water attorney, and so he was speaking about water from the humanities angle. And the second speaker was Rhonda Salem, who's the manager at the Metropolitan Water District of Southern California. And he was talking about water from a social sciences perspective. And tonight we have Richard Denton speaking from the engineering perspective. And so with Professor Sakeley, he's going to be talking about water from natural resources, natural sciences perspective. So I think it's really going to be a great lecture, and I hope you all come to that. So at this time, I'd like to Professor Robert Weigel to introduce our speaker.
I'm really pleased for the opportunity to introduce our guest speaker today, Richard Denton. I've known him ever since he came to the U.S. This is what, 15 years ago. I probably did a little bit before that because I read the papers.
20 years.
And he did both his undergraduate and his graduate work at the South Island of Australia. That's Tasmania. New Zealand. No, it is a joke. If you go to Tasmania, they talk about the North Island being the rest of us. And Richard did his work there and got his PhD, and then he went to Germany and spent 3 years as a research engineer working on water problems. And his main specialty, I mean, he's of course a hydraulic engineer basically, but in the mixing processes, the water quality, how it mixes, density flows, and things of this sort. And of course, this is an ideal background if you end up in working for years on the problems in the Delta region of California. That is the San Joaquin, Sacramento river system. It's an extremely complicated type of problem of fluid mechanics. And it's rather interesting because my tenure here overlaps with O'Brien, after whom this building is named. And in the early 1930s, I think about 1932 or 3, O'Brien performed a small experiment, not in this building, it wasn't here, but in an old building which had a small hydraulics laboratory. And the test that he was doing was what would happen if you built a lock and a dam between the Sacramento River and part of the Delta, and you try to see what would happen if you opened it and closed it at different tide levels, not just the levels, but because the salinity would be different, to try to separate out the fresh water from the salinity. And I got interested in the history of fluid of these types of things, and as far as I know, that I can find, that was the first use and the invention of what we call the dense elementary fluid number. And there was published in the ASCE, and then one of the discussers was Garvis Cooligan. And Garvis Cooligan in the discussion really worked out all of the dynamic similarities showing why this number should be the controlling number to do this sort of experimental work. So there's been a long history in here. And it's partially because of that, also because I like Dick, that I wanted to have this opportunity to introduce him. I won't take any more time on doing it. He's had many publications on the scientific and technical engineering aspects, and now Of course, like many good, successful engineers, he's now a manager. But we hope that we won't lose him as a good technical engineer because he's a manager now. Okay?
Thank you, Professor Weddle. Yeah, it's a great pleasure to be back here because I was teaching here for about 7 years, starting in about 1982, and this is the room that I taught in, so come back home again, I guess, from that point of view. It's good that we do have this new technology, and it's also good that it's working tonight, because it's always dangerous when you decide to move from using overheads to using a PowerPoint presentation that the computer plays up on you. Can you all see through this? Or should I move it over? So my talk today is just understanding the delta, looking at it from an engineering perspective, rather than say a management or a chemistry or a biological perspective. When you're talking about the delta, really the delta ends at, legally it actually ends right at this point here. So what we're talking about for the delta is the inflow from the Sacramento River coming from the north, and the inflow from the San Joaquin Valley along the San Joaquin River from the south, and meeting at this point here at the confluence, and then flowing into San Francisco Bay, which is this area here, through Sassoon Bay and through San Pablo Bay, and then connected to the ocean. So in understanding the delta, we're talking about, like all deltas of course, is that you're getting a freshwater inflow, a less fresh water inflow because its return flows pretty much from agricultural practices in the San Joaquin Valley, and you're having a mixing process with the salt and the exchange with the ocean at this point here. So as Professor Weigel said, that at times you do in fact have these kind of density currents occurring. If you have very high flows coming down from the San Joaquin, from the Sacramento River, it can float on top of the salty water that's already in the bay and then head on out in this direction here. You've got tides going on and up and back and forth, but usually there's enough fresh water for it to float up on top. But the usual situation in the bay is that you have strong mixing over the vertical. So what you would do is if you drew a line coming along something like this, you would end up having 35 parts per thousand salinity or ocean salinity here. And as you work your way up into here, this region here, you're getting down into the 10s and the 2s parts per thousand salinity. So there's a gradient, a horizontal gradient of salinity. Go to the next slide. So when you're talking about the delta, you need to talk about the delta from a political point of view and just as much as an engineering point of view. And so when you're talking about the delta, and this is sort of a rough outline of the delta, maybe it's a little too large an area, as I said, that the delta really clips off at about this point here. But there is the delta again with Sacramento, San Joaquin, but really the people in this whole area here are affected by what goes on in the delta, how we operate the delta, how the fisheries issues are handled, and how the engineers are brought in to try and deal with some of these issues. And so you're talking about a situation where you have a lot of rainfall in Northern California, very little rainfall in Southern California, but a big population base there and a big agricultural base here. So the idea is to get water from here to agriculture and then to the urban areas, and the delta is really the sort of the choke point, or the position where you're trying to get water through. So next please. I talked about all the various rivers. As I go through today, I'll be talking about various engineering projects related to the delta, and as I do that, I'll be talking about some of the dams that are on these rivers, and be talking about the various influences of some of these rivers, the various flows coming in and making up the flow out of the delta and into San Francisco Bay. This is a highly developed system, of course. You have a lot of dams in the north where the rain falls. Some of those dams belong to the federal government, were built as part of a federal project. So you have Shasta Dam up here. You also have over on the Trinity River, you have Clare Ingle Dam, which contributes to the Sacramento system through a system of engineering piping. You also have the State Water Project, which is Oroville Dam, which provides water, releases down into the delta. And then you have a way of picking up that water and moving it down into the areas where it's needed in Southern California or in the Central Valley. There's also some local projects some notorious and some other. You've got the Los Angeles system taking water down to Los Angeles from the Owens Valley. You've got East Bay Mud takes its water through an aqueduct to this area, and you have the city of San Francisco taking water from Hetch Hetchy and moving that through the San Francisco region. Next, please. So again, from a political point of view, the Delta is very important. It's a source of drinking water. I'm putting that up front because I work for the Contra Costa Water District and we provide urban drinking water, so that's my main issue in terms of the main thing that we look at in terms of dealing with the Delta. We also have a lot of plant and animal species that's supported by the Delta. It supports the agricultural industry south of the Delta. There's a lot of, obviously, housing and infrastructure within the Delta. The Delta is important in terms of fisheries, both fisheries that are resident within the Delta and fish that come in from the ocean, move up through the Delta and up into the upper tributaries. They have to move through the Delta where they're susceptible to pollution, to pumping, diversions in the Delta, etc. And it supports California's $1 trillion economy. So whenever things are going wrong with the Delta and we're ending up in a situation where either fish are being hurt or there's not enough water for the farmers or the urban areas, a lot of people go back to Washington to point out that this is a large economy in California and we can't let them do without water, and of course more recently we can't let them do without energy either. Next, please. So again, from an engineering perspective, if you're looking at the Delta, you can break it down into the main flows of the Sacramento River coming in. What I'll be talking about later on is some of the plumbing that's been done to the Delta, and there's a little channel here that takes water out of the Sacramento River where it would normally go and feeds it into the central Delta. So that's why I've just shown the two arrows. And we'll come back to that later on. And again, you have the San Joaquin River coming in from the south, and I've colored it a different color because it's got a lot of agricultural drainage, pesticides, a lot of extra salt in it, so we need to watch out where that water goes. And most of the time, which is to the fortunate for some people, not for others, is that a lot of that water that does come from there gets brought over to the very large pumps, the export pumps in the South Delta, and then recirculated back down to the Central Valley. However, from Contra Costa Water District's point of view, we have these three intakes here. What we're concerned about is what is the effect of any agricultural drainage and pollution like that coming into this area. There's some seats up there. So again, a lot of the issues that we'll be looking at is as you step in as an engineer and say, we can fix this problem, we can pour concrete and so on, you need to think about all the other effects of pouring concrete or doing those sort of hard engineering solutions on the fish, on water quality, and so on. Next, please. Again, just a little unashamed advertising for the district that I work for, but just it also puts in perspective a little bit of why Contra Costa Water District's so involved in Delta issues, is that we are right there beside the Delta and we take our water from the Delta. So anything that's going on in the Delta in terms of degrading water quality, that affects us immediately. So we're the most affected by it. East Bay Mud, for instance, is not affected by what's going on from the Delta because they take their water through a pipe all the way from the mountains. And if fisheries issues crop up, that there's problems with the fish and we need to shut down pumping, then obviously that's an effect on us as well because it cuts down on our water supply. So later on I'll be talking about one of the engineering projects we put in, which was this Los Vaqueros project and a new intake. Actually, I put this in the wrong spot. That dot should be over here. On the river. This is our transfer reservoir, not our intake, but our intake's over here. We built this new intake so that we wouldn't be dependent on this intake here, which is a little bit saltier in terms of water quality. Okay, next please. And again, when you're dealing with the Delta, you just need to look at these in perspective that most of the water going into the Delta does come from the Sacramento system. So there are other supplies of water from the east side streams, the Calaveras and Calamy, etc. This one here, the Yolo, is really just a flood bypass, so it's really Sacramento River water, but it comes in through a special bypass to avoid flooding in the Delta. And again, rainfall falling on the Delta itself really doesn't contribute very much. So that's really not something you count. And this one, actually, I got this from the DWR Delta Atlas. I'm actually surprised at how large that is because there really isn't a lot of water from the San Joaquin that comes into the system. And if you're looking at the delta and what we're trying to do with the delta, I've developed these just based on Cal-Fed Bay Delta program goals. And the Cal-Fed Bay Delta program was started in about 1994, maybe 1995, where all the various interests got together and the various agencies that are working on the delta, the federal and state agencies, and said, the way we're doing things is we're doing it piecewise. We're trying to protect one fish over here, we're trying to fix up water quality over here, and it's all disorganized. We need to have a program that looks at this as a whole. And so the Cal-Fed is really made up of Cal for California and Fed for federal, and the agencies all working together, or hopefully working together. So the goals are really just water quality, ensuring that we have good water quality, and that water quality can be used for fisheries. We don't want to have pesticides in the water to kill all the fish off. It can be used for drinking water, so it provides drinking water for about more than 20 million people, the water from the delta. For agriculture, it really can't take too much salt in its water, but it can handle a lot poorer quality water than urban drinking water agencies. We need to restore a sustainable ecosystem in the delta because of all the resident fish and the fish passing through the delta. We need to reduce the mismatch through water supply and demand, and that was very well crafted by Cal-Fed, the way they talk about the mismatch. Because from a water user point of view, we usually say there's not enough supply, we need to develop some more. But then from the other perspective, the environmental organizations step in and say, well, you can also meet the difference between supply and demand by reducing the demand. And by doing a lot of things like conservation, recycling, water transfers, things like that. So the idea is to reduce the mismatch between water supply and demand, and you can do that through all of those things, developing more supply and doing more conservation. And the other one that's important that sometimes people forget about, is usually they talk about these three, but improving the structural integrity of the delta levee system is important because the delta was essentially reclaimed by building a series of levees and creating channels. Before it was just a big swamp or a marshland. Once you build those levees just out of muck, essentially it was built out of muck, not in the way that you as geotechnical engineers would design a levee. So basically they're in a situation that if you touch them, you break them. And that actually happens a lot. Someone gets out there and decides to pour a bit more dirt on it because it's starting to subside a little bit, and then the whole thing fails. And if the levees fail, then what happens is that, like Professor Weigel was talking about, it, you're essentially creating a hole, so then the sea rushes in to fill that hole, and all the salt rushes in with it. And that happened in 1972. There was an island, Andros Island, failed. And normally, at rocks, at the CCWD's intake, we're trying to keep the water quality better than 250 chlorides. When that happened, the chloride shot up to 472 milligrams per liter. And it persisted for several weeks and then slowly died down again. So in a big earthquake, this water supply for 20 million people and for agriculture could disappear because the levees could fail. So again, that needs to be looked at as well. So some of the things I'll touch upon today, I'll go into a little bit more detail with sort of case studies, I guess, on some of these issues. There's different ways as we as engineers can roll up our sleeves and say, you know, we can solve this through concrete and building hardware. One way of doing it is to build barriers in the delta to move flow in different directions, to try and improve water quality that way. We can also build barriers to keep the fish in the larger river systems rather than letting them stray into a different river system where they might get lost and end up heading in the wrong direction. And you also have barriers for water levels, and I'm thinking there down in the South Delta. Down in the South Delta you have these huge export pumps. When they turn on, essentially they drop the water level because of just the need to pull water out of that area. You need a hydronic gradient to get the water flowing. And well, the other way of looking at it is just there's only a certain amount of water you can fit into the South Delta. If you suddenly start pumping it out, it just drops. So what they're thinking of doing is putting in some permanent barriers in the South Delta to artificially keep the water levels higher in some parts so that the farmers in that area can pump that water out and continue their irrigation of their fields in the South Delta. So I'll touch upon that a little bit later on, about what's good about that engineering and what's bad about that engineering. The other way to achieve, say, the water quality goals or the fisheries goals is just to increase flow. And that's a tough one, because you might say, well, let's release some more water from our reservoirs, but you've got a finite resource, so that you could, if you dump it all at a certain time to protect a certain type of fish, come another period of the year when another fish is endangered, you've got no water, and you've got no water for the farmers in the urban areas either. This one I threw in here, the San Joaquin River recirculation study. There's a problem in the San Joaquin River that it gets too salty at certain times of the year. So one thought that came up is that why don't we just pump water from the delta all the way down through the Delta-Mendota Canal and the California Aqueduct, do what we normally do to get water to Los Angeles and to the San Joaquin Valley farmers, but once we get it all the way down there, then we just let it flow back down the San Joaquin River. And that initially seemed like a dumb idea just from the energy point of view back then. It seems like an even worse idea now because of the energy situation. But again, that's something that we may, as engineers, solve the problem by throwing a lot of energy and might at it, or engineering at it, to actually move water around. We're already doing that. We're already taking water from the upper Sacramento River and moving it with pumps and canals and all the way down to Los Angeles, but this is just another version of that. Fish screens and fish salvage. That's another way of trying to protect the fish, because when you turn on large pumps in the South Delta, there's a tendency for the fish to head in that direction, or if they're already in that area, then they'll get drawn into the pump systems. So there's a lot of work going on within CalFed and other places to design fish screens that actually work. And that's the tough part, is that if you have a fish screen at the end of the funnel, the fish are going to move towards it, they're going to smack up against it, and there's nowhere for them to go. So that in a sense is a poorly designed fish screen, and that's what we have at the moment for the export pumps. And so what they do is they have little bypasses and try and salvage the fish, put them in a tanker truck, and then drive them back into the delta and drop them back out again. And that again is not a sustainable or very sensible idea, because you're handling these fish, you bring them into a hot, warm water in a tank, and you dump them along the road, and then you put them out in the delta, where a lot of very bright scavenger fish are waiting, and because they know it's feeding time, and then they get eaten. So obviously when you're designing a fish screen, you need to design it somewhere where the flow is going by tidally and you're taking the water out sideways so the fish can keep moving by. So that's the goal of some of these, and so I'll try and touch upon that as well. New or improved conveyance. One way of solving your water problems is just to build bigger pumps, but then that just exacerbates all the other problems that are there. One way maybe is that bigger pumps are somehow seem to be drawing fish towards themselves through narrow channels, then maybe you can make the channels wider, do something like that. Another solution that we engineers come up with is that we need new or expanded storage. In other words, capture high flows when it's raining in the wet periods, capture that, store it in a reservoir, and then release it later on. So that's another goal, is to develop some storage to go together with some of the other actions that are being taken as part of fixing the delta situation. One way is to store that water in the ground. One problem with that, in a sense, is that you can't capture water quickly enough to put it into groundwater. It takes time for it to seep in or for you to pump it in. So it's good to have some sort of a reservoir system to put the water in and then feed it into the groundwater system. There's a big debate about whether you want off-stream storage or on-stream storage. An example of on-stream storage is Auburn Dam, which is a big no-no. Most people oppose it except a few people in the Sacramento area. But the idea that is coming out of this CalFed process is that at least if you're going to have storage, then and surface storage, then it should be off-stream storage. But that in itself causes a problem, because then you have to pump the water out of a river up into that storage, and you get into energy problems again. And then another one here is just in-delta storage, that you can maybe take some of the sunken delta islands and put water on those islands, and then release it later on once the flood waters have gone by. Okay, thanks. So I was sure that, just to give a balanced presentation, I just wanted to point out that the last part there was talking about let's build some more dams. And as you can see from this graphic, which again came from DWR's Delta Atlas, I think, is that there are already a lot of dams in California, and the environmental agencies have been very quick to point that out, and in fact, at various times there's been actions to actually take out dams, ones that are blocking migration passages for fish. So we have a lot of dams, and so we really do need to look at it from the other side of looking at softer solutions to this problem. So this is the, well, some of us call soft path proposals, and other people would call sensible proposals, but they are, you know, all valid solutions to this problem, and they all need to be built together with the hard engineering and the soft engineering approaches. So one is that if you're worried about water quality, don't just try and solve it with barriers moving the dirty water in one direction and the good water in other directions. Maybe you go upstream and you try and find the sources of agricultural drainage and other sources of contamination going into the delta, and you protect your watersheds. You look at the erosion that's caused when you cut down forests and things like that. So there's a very strong watershed protection program within CalFed as well. The other way is that if you're worried about the water in the delta not being good enough to drink, the usual reason, or the reason for that, is one, it's a little salty to the taste, so you might need to worry about it from that point of view. But unfortunately, there's other issues involved with, if you have pathogens and a lot of the different germs that might be in the water, you first have to disinfect that water before you serve it to your customers. And as you get further and further into what kind of pathogens are in the water, you need to dose it with more and more disinfection over time as the standards become more and more stringent. And what we're finding is that the more you disinfect, the more you produce byproducts that are cancer-causing or suspected to be cancer-causing. So EPA then steps in and said, first we want you to get rid of the germs, and at the same time we don't want you to produce too much or too high a concentration of these disinfection byproducts. So there's a balancing act going on that you need to get rid of the germs and the pathogens, but at the same time you don't want to be producing too much of these suspected carcinogens. So another way of doing it is using some sort of disinfection that doesn't produce the problem disinfection byproducts, and that would be ultraviolet disinfection. And that's something that is being used in the wastewater industry, but not so much in the drinking water industry, but it is coming in a big way. So that may be part of the solution, is just to find a different way of disinfecting so you don't have to produce as many byproducts. And the point, I guess, the point of this is that the byproducts that you produce are directly proportional to the salinity of the water that you're disinfecting, and also how much organic carbon is in the water. So you have, depending on what's in the water coming into your treatment plant and how much disinfection you apply, gives you the concentration of disinfection byproduct. And unfortunately, the delta is a bad place for that, because there's a lot of peat soil, so there is a lot of organic material in the delta. So you're starting off in a bad situation. You bring a lot of, or you're stuck with a lot of organic carbon in your water. And also because it's connected to the ocean, then you've got the salinity there as well. So that's, again, why we need to be looking at the way the flows are going on in the delta to try and keep the salt out and also minimize the organic carbon that's in our water. So the way you can, maybe another way of dealing again is with membranes, that if you push the water through or move the water through high pressure or low pressure membranes, you can take out, if it's a high pressure membrane, you can actually take out salt. If it's a lower pressure membrane with just larger holes essentially, you can actually take out some of the pathogens and the germs, and therefore that reduces how much disinfection you need to do. So this is something that's being raised, that, you know, why build large reservoirs to solve the drinking water problem when you can do some of these techniques as well. So I think there's going to end up having to be a balance between the two. You do some of this and also develop some storage. Similarly, improved water use efficiency, conservation, reclamation, so reusing the water. And I put water transfers in here. I don't know what necessarily exactly belongs there, but at the same time, we need to be using our water more efficiently, moving it from people that are wasting it to people that can use it more efficiently, or higher yield in terms of productivity, etc., etc. But again, that's a very political decision to do that. You want to let the marketplace maybe decide that. If water's not being used profitably, then if you set up the right market situation, then that water will be transferred. And then on my previous slide, I talked about the removal of adding barriers, but here's a situation where you want to try and solve problems by taking out dams and removing barriers to fish migration so they can go out to the colder water and spawn. And also there's a lot of wetland and riparian habitat restoration going on around the delta. where you reclaim areas, you allow the tidal action, you allow water to get in there, provide habitat for the wildfowl and also for aquatic species. The only problem with that, and as the Contra Costa Water District sometimes leaps up and sort of is a skunk at the party and saying, this is great, you're helping fish, you're helping everybody, but we're going to be careful because these areas are very rich in terms of nutrients and organic carbon, and so whatever they produce in terms of additional organic carbon gets back into our drinking water problem. So, there needs to be a balance on that as well. Okay, just in terms of the barriers and tide gates, maybe just going on to a couple of engineering examples. One is the Delta Cross Channel, which I talked about earlier with respect to the splitting of the Sacramento River. That there's a channel that was built by the U.S. Bureau of Reclamation to take water out of the Sacramento River and feed it more efficiently into the delta, to freshen up the delta. The only problem with that is that it improves water quality, but then it also can move fish out of the Sacramento River on their way out. So they're moving down from Shasta Dam back out to the ocean, then they can get lost within the delta if they move with the water into the delta. And then the other one is the South Delta Improvement Program that I talked about before, that we want to develop higher water levels when this pumping's going on, the export pumping, so the farmers can divert water onto their fields. We want to block fish that are maybe moving up the San Joaquin River or down the San Joaquin River into the delta. We want to stop them from being sucked across to the pumps. So we might want to put a barrier there to block the fish from going straight to the pumps. And also we want to improve the circulation in that area so the water isn't too salty for the farmers. Okay. So here's a photo of the Delta Cross Channel, just an overview. It's looking south, so what you're looking at is the Sacramento River coming down here, and here is the cross channel. There's a couple of radial gates there that would feed water into this system, and then it's off on its path down into the central delta through these channels here. If the cross-channel gates are closed, the water can still get into the delta through the Georgiana Slough here, but it's much smaller. So by shutting off this artificial channel here, you significantly reduce the water is getting into the delta through Georgiana Slough. And the way the photo is taken, you don't really think that this doesn't look very impressive, but this is where the Sacramento River continues on and on. So this is in the area of Walnut Grove here and the town of Locke, this region here. Here again are just the radial gates that just so they can be closed, and they're closed at certain times of year to prevent flooding and also to prevent the fish from straying. Okay, so I've talked about this pretty much. Is that it's designed to increase the flow of fresh water into the delta. It's closed at times for the delta flooding issue. We do get this out-migrating salmon and other fish straying through there. It's closed according to the State Water Resources Control Board regulations for a certain number of days per year, that's in certain months. And then the key thing I want to talk about today is that in October and November of 1999, the fisheries agencies were watching, and they noticed that there were a couple of fish showing up further up on the Sacramento River. So they requested that the cross-channel gate get closed so that when the rest of the fish start moving, that they will be able to move past the cross-channel without going into the delta. But unfortunately what happened is it was at a time of very high delta pumping, very low delta outflow. So when they slammed the gate shut, suddenly the water quality in the interior delta, this concentrations also shot way up. And I'll show you a graph of that in a minute, but this became a kind of cause célèbre because it was at a time when there was a lot of arguments going back and forth between the fisheries agencies and water purveyors. And so what the water agencies saw this and sort of said, here they go again, see what all the damage that they're doing to us. And they rushed back to Washington and sort of said, we've shut down Silicon Valley because you closed this gate, essentially. Okay, so next slide. And this is just an example of some real data showing what actually happened at that time. Here are the chloride concentrations that were occurring before they shut the gate. Then they shut the cross-channel gate at this point, and you can see from the blue triangles that the water quality shot way up. And you've probably forgotten that, remember at Rock Slough where we take our water, the standard is supposed to stay below 250. So that projects who are operating the delta have to arrange to have the right amount of flow going through the delta at all times, that it never exceeds the chloride of 250. But because of this action, it suddenly shot up and overtook the 250 standard, and the standard was violated for a short period of time. And this we put in here from Professor Sobey is these two results here are actually from a computer model of what went on. And again, if you ignore this just for a second, I'll come back to that promise. What we did is we started from way back at this point in time. We put into the computer model the flows that we were estimated to be occurring in the delta at that time. And so the caveat is that do we really know that those flows were there? Do we know how much water is being evaporated, how much is being taken onto local farms in that area, how much was really coming out as delta outflow? So that was calculated, and as we went through, then we did one run with the red line for closing the cross channel and one with the leaving it open, just to show that this was in fact a bona fide effect of closing the cross channel. The trouble with the delta is you never know what would have happened if you hadn't done what you did, because as one of my colleagues always says, there's only one delta, so you don't have your control case at the side that you can compare against. So you do have to do this with modeling. And so again, we got this similar sort of rise here that we did see, but if it hadn't closed, then we would have got something like that. So the next part then is, and this has really brought people together to say, well, is there a better way of doing this? Is there a way maybe of closing the cross channel only for certain parts of the tide so that we can protect the fish when they're moving through on a certain phase of the tide? For instance, when the flow is ebbing out of the delta in the downstream direction, then maybe that's the time when the fish move, then you close the cross channel then. But when the tide changes and the water comes back up again, maybe we can open the cross channel, squeeze some water into the water without fish into the central delta and keep the freshening effect going. So that was a test that's been done recently. They did it in the beginning of 2000, last year, and so we're still analysing the results. So what is the effect of just closing the gates on the ebb tide? And what they found is that if you just do it that way, it really isn't any impact on water quality. So you've got to then back that up with saying, well, what is the impact on fish? Is that still hurting fish because the gate is open some of the time? Some of the things they've been doing, and they've been doing a lot of very detailed monitoring out there for the fish, is to do the fish move during the day or nighttime. And they suspect that maybe they move during the nighttime, in which case then you would only have maybe the gates open for just one part of the tide, the part of the tide that was flooding during the daytime, so that you would be protecting the fish more. And when you do that, you do see some impact on water quality, but much less than if you had just closed the gates completely. So this is still going on, and if you have the gates open for 6 hours of the day, what's that do for water quality, and is that being overprotective for the fish, for instance? So these are interesting experiments that are going on. Okay, the South Delta Barrier Program, we'll skip to the next one. I talked about this in my previews. I'll talk about it in terms of the graph. So what the DWI is planning on doing, and in fact has been planning on doing for about 10 years now, and in fact in about 3 draft environmental impact reports, is trying to come up with permanent barriers at various places, these 3 places here in the South Delta, to keep the water levels in this part of the South Delta higher and compensate for this barrier that everyone agrees should go in there for certain parts of the year to stop the fish that are coming down from the San Joaquin River, to stop them from getting sucked across to the pumps over here in this region here. So what we'd like to do is shut this at certain times of the year, move the fish on out through the delta. But once you do that, then the water flow going into this area is reduced, and the drawdown is increased, and the salinity in this area goes to heck. So what they want to do is put gates in here that allow water to flow in this direction from west to east, but not in the other direction. In other words, keep the water level up. And they're also doing other things like dredging channels, etc. in this region, which makes us real nervous because our intake is right there. And then at the same time, as part of all this, they want to do that because they want to increase the pumping out of here. So not only do they want to correct an existing problem, they want to be able to move forward and increase their pumping and still improve things. One of the things that we are concerned about, and it's not immediately obvious when people are talking about this, is that if you do block off all the flows in this region here, maybe you can improve circulation in this area, improve water quality for them, but then what if this bad water coming down here, where does it go? And unfortunately what happens is it circulates around here and hits us first. So these guys, they would get a slight degradation as well by the time it circulates all the way through, but unfortunately it hits us first. So what we propose is if you're going to go ahead from an engineering point of view to build these barriers, increase pumping at these locations, you need to do something in this region here to offset the impact of water quality at our intakes. So there's another project going on to reduce the effects of agricultural drainage or local drainage from these farms and these islands here near our intakes, so that we can offset any impact of this circulation or redirection of water quality impacts. And part of my list before was just saying we had different things we can do. We can put in barriers, we can increase flows, we can also convey water differently through the delta. If the delta is the bottleneck, then let's sort of open it up so we're not choking the flow coming through. So the various proposals that have been suggested, and this is before my time, so I don't take any blame for that, was the peripheral canal, and I'll talk about that in terms of the graph in a minute, or the map in a minute. That was defeated soundly by the voters in 1982, so then everyone went back to the drawing board to see what they could do. More recently, as part of the CalFed, as CalFed was developing their various alternatives for solving the delta, ideas came up about, well, let's take the levees, which are already crumbling anyway, set them back, and then you've got wider channels, less flow, the fish will have places to hide along the banks. You know, we can create some riparian habitat. They won't get drawn as easily down into the south delta of the pumps. Then there was another one that was chain of lakes, which in a sense really wasn't as much, well, it was a combination of conveyance and storage. In other words, you take a whole series of the islands in the delta and just use them as reservoirs. And if you're a good engineer, you can somehow build a siphon between those lakes and move the water as a cascade all the way through the delta. I think there was a lot of big issues there, that these things are sitting down there in peat soil, they're just going to float up. So how do you hold them down so they're not going to float away, the siphons between the chain of lakes. So this thing was hugely expensive and got dropped almost immediately. And then I'll talk a little bit about where CalFed is right now. And then the other one I put in here, just it may look like a joke, but it keeps coming back every now and then, is they've talked about putting water in bags up in Alaska and bringing it down the coast to help our needs. And the person who's suggesting this threw it in recently as a way of moving water from the upper Sacramento. He would fill them up further up by Redding, somewhere like that, tow them down the Sacramento River and discharge or empty the bags somewhere near one of our intakes in the Sassoon Bay area. But then if you did the math on that, you'd have these huge bags that are 200 feet long trying to maneuver their way down the narrow rivers. And then I think the calculation is they'd have to be moving in, offloading, and moving out every 16 minutes or something like that. So, you know, it's something that really wouldn't work. And unfortunately, this became a little political because it was something that was sent to various politicians. And so the way we combated that is saying, well, how's that different than this? You're taking water out of the delta, moving it to a point south of the delta without allowing it to move through the delta and benefit fish as it's moving through the delta and benefiting water quality. So the peripheral canal was a bad idea because for one reason it's 29,000 CFS capacity. And when you think about it, a lot of the operations that are going on with the delta at the moment, you usually have, say, around about, you're lucky if you have about 15,000 CFS flowing down this part of the river here. So it kind of doesn't compute if you have a large intake like that trying to take water out and let more water out that's coming in. So that wasn't going to work anyway. I think they wanted to build it large enough so that when there were flood flows, they would have the opportunity to take it. But of course that makes people real nervous that if you have a large facility like that, how's it going to operate? And so what they would do is just put water in a canal, move it around here, and then pump it away. So that got defeated soundly because it was really getting people away from what they call the common delta pool, the idea that everybody should have a stake in what happens to the delta in terms of are the fish thriving, are the delta, the levees stable, and is the water quality good in the delta. And if you're getting your water out of the end of this canal, then you don't really care what's going on here because you're independent of that. Okay, next. This was the one about the true delta alternative that some of the urban agencies were thinking about, is if it really is a perceived problem that fish get drawn along these narrow channels here by the flow, the mean flow down to the pumps, then why don't we take an island, inundate it, and don't go telling people we're going to inundate this island. It was just an illustrative example. You might know someone has a holiday. But what you would do is inundate an island, and you'd be able to create some habitat for fish. Some of these islands are very deep, so maybe it's not shallow enough for fish, but you can work on that. And what you would do is just basically create a channel which is still connected to the delta and still tidally bearing, but you would have a way of having slower moving water moving down into this region here. So that was suggested, but it really wasn't taken up by the CalFed. What CalFed ended up doing was, you can see here, they did a few of them. They said channel enlargement, possible modifications around here, widen the channel a little bit, but don't actually inundate any of these islands. And then they still have on their alternative these south delta barriers that I was talking about. And then something that did creep back in, it's not in the immediate preferred alternative, but it is going to be studied, is a little bit of this idea of pumping water out of the Sacramento River. It's not going to go all the way around to here, but it would be a way of injecting water a little faster into the interior delta instead of just letting it move in through the delta cross channel, which is located here. Okay. Here is another one that got thrown out, and again this is sort of engineers brainstorming, trying to be biologists as well. But this is one that we got put out there, and really where it came from was that they have a lot of problem with the fish screens in this region here, because again it's at the end of several large channels drawing the fish down into that area, and they've got nowhere to go, so you really can't screen them safely. However, our intake here is on the side of a channel which has flows, tidal flows of say 10,000 CFS, either moving back and forwards, or also in terms of the net flow through here is also about 10,000 CFS. So you have that tidal exchange going on, plus you have net flows sweeping by, and at the same time then we are taking out of here about 250 CFS. So really we're taking out very little, but we're taking it out very little from the side of a large flow. And what we find is at certain times of the year, they end up taking tens of thousands of delta smelt, for instance, which is a resident fish in the delta. When they're taking thousands per day of delta smelt, we in 3 years of sampling in this region have taken one. And so we're saying that this is obviously a smaller intake than what we're talking about here, but it's on the side of a river. It's got the flows. The fish aren't going in this direction against the screen; they're going past the screen. And there's really no horizontal flow, very small velocity towards the screens. So why not try and improve this system here by actually building largest pumping or intakes up here, which somehow get piped or through natural channels down into this region here. So you would design up on a larger arm of the San Joaquin River here, some screens that were on the side of the river where there's sweeping tidal flows. And so we threw that out as an idea, and then saying maybe you can also build a bit of storage on this island here and try and put all that together. And again, that was something that maybe caused a bit of commotion at the time, and people looked at it, but it got eventually dropped from yeah. But really what you're trying to do is look at what the fish need, look what the water quality needs are, because this is still a good water quality area, and then also trying to meet the water supply needs by somehow making these, designing pumps that can operate more often at a larger capacity, so you're not shutting them down as often. Because that's the other thing that I really haven't discussed as much, is that you may have these huge pumps here and they may be a concern in terms of the fisheries, but at the moment under the biological opinions and the operating criteria for these, some of these pumps just get shut down almost dead for long periods during the springtime, for instance. And so that is something that obviously the water users are very concerned about, because it represents a loss of water supply. Okay, so we're moving on to looking at the new or expanded storage. What I'll do is in a minute talk about Los Vaqueros Reservoir, which is a reservoir that CCWD has completed just recently for water quality purposes, and the thought is that maybe that's something that could be expanded, and if it's working well for CCWD, maybe we can build it bigger and make it work for East Bay Mud, Santa Clara Valley Water District, and also Alameda County Water District and various other water districts in the Bay Area. Another one is just to add 6 feet to Shasta Dam, and that could produce up to 300,000 acre-foot of extra water. Maybe, I don't know whether you're used to 1,000 acre-feet, but Shasta Dam at the moment is about 4.2 million acre-feet, so you're not really adding a lot to it, but again, this is a large supply in terms of helping to meet the deficiencies in agriculture and urban supplies. The usual number you see in the newspapers is that 1,000 acre-foot is enough to provide water for 1 or 2 families for a year. In delta storage, I mentioned that you can take some delta islands and flood them, and there's a proposal that just got permitted by the State Water Resources Control Board to go ahead and do that. It's going to be a very expensive project, and so it may not go ahead eventually, but considering that. And then there's an idea of building up north on I-5, north of Sacramento, is a big off-stream reservoir which would bring in a lot more water. And that could be used for water supply and for fisheries needs. And then you could also expand some of the reservoirs in the San Joaquin Valley further down, or you could go to groundwater storage. So these are all proposed as part of this CalFed program, so they're not ones I'm just making up as a good idea. Okay, so this is our Los Vaqueros reservoir as completed and as pretty much full. It's only 100,000 acre-feet at the moment, and remember I said about the idea is expanding it from 100,000 acre-feet capacity to 500,000 acre-feet. So what you will need to do is actually take out the existing dam and put in a new dam at a larger level. So if any of you are geotechnical engineers, you can't just start piling concrete on top of it or dirt on top of the existing dam. It wasn't designed to take that. So we're going to have to, if this does go ahead, they'll have to take it back out and put a new dam back in. And so what the uses, maybe the next slide is. Oh, yeah, this one you saw before, but this again is where this reservoir is, and it's filled from this point in Old River, and then water is released from there down into our service area and provided to our customers. Thanks. So again, it's designed to store water, and what we do is we store good quality water in there, and then later, at different times of the year when the delta water quality is not as good, we can actually release water from our reservoir and blend it with the delta water quality and meet our new water quality goals. So what we're trying to do is meet a 65 milligram per liter chloride delivered goal. And as I said before, the delta can go up to about 250 chlorides according to the state board regulations. So we have to have enough good quality water in there that whenever it does do that, we can release water from our reservoir to blend it down to 65. And 65 was designed back before some of the newer regulations are coming in terms of drinking water quality. So I think if we start again, we may be asking for a better water quality coming out of this system than just the 65. And it also provides ecosystem benefits because at certain times of the year we can use that reservoir to meet all our demands, which means we can get off the delta completely in terms of pumping from the delta. So if there is an issue with fish being moving through the delta or being close to our intake, we can actually shut down periods of time. And that occurs naturally anyway, because usually when we'd be releasing water from our reservoir to blend to get good delivered water quality, that's usually the time when you've got low flows, therefore high salinity in the delta, and then the fish are more susceptible at that time anyway. So automatically, because we have this reservoir and we're operating for water quality, we tend to get off the delta when it's most important for the fish for us to be off. And again, this, we were joking before, is usually talk about these projects being about a 10-year project. And so we started working on it in 1987. It took these 7 years or so to get the permits necessary and get people to agree that this could move forward. And then the reservoir was completed in 1998, and when it was completed, it was the first reservoir completed in California in 10 years. Up till then, EPA was being very skeptical, essentially, of new reservoirs. They were sort of saying, well, you need to prove to us that not only are you not going to harm anybody, but you can actually provide some benefits. And you also need to show that you're not wasting water, therefore just building this to meet your wasteful needs. And so we had to go through a lot of hoops to get this far. And the only other reservoir of a major size that has been completed since then is Metropolitan's Reservoir in Southern California. And the last speaker that was here, Ron Costello, talked a little bit about that. So this was interesting. That January 1999, we managed to get the reservoir full in a year. Beforehand, we did all our planning, modeling studies, looked at the hydrology and various things, and looked at the water quality, and determined that on average, or is most likely, that would probably take us about 3 or 4 years to fill. But luckily, we were able to get the reservoir completed just during a period that's been remarkably wet. So we were able to go ahead and fill it very quickly. And we did actually end up getting an award from ASC as the Outstanding Civil Engineering Achievement for 1999. And that was based on all the environmental aspects that were built into it within the watershed itself, and just the way that the reservoir was designed and operated. So that's where we were. Now, of course, someone stepped up and said, how about we make it bigger? And so this is going to be fun for us as engineers to first sort of see if this is even feasible. And so really what I put up here is that we're moving forward now on the idea of studying this. Nobody said that this is going to go ahead or it's an acceptable thing to do, but there's no harm in studying it to see what could be done. And so we are actually, because we want to maintain local control, or at least control over our own reservoir, we have contracted with the California Department of Water Resources to actually start performing these studies. So this is going to be a 7-year process pretty much before people start pouring concrete or compacting dirt, or even pulling down the old dam. So this is going to be a long time. But we are looking at this as what happens if you did expand Los Vaqueros. You have more water for local uses in the Bay Area. And there is another part of CalFed, which is another project, of saying we need to look at not only just new storage in the Bay Area for water quality, but maybe East Bay Mud could use their pipeline to deliver water to Alameda County, something like that, to improve the water quality for Alameda County. Because San Francisco gets their water from the Sierras, East Bay Mud does, but Alameda and Contra Costa and Santa Clara all get their water out of the bottom southern delta. So they're all susceptible to these water quality issues. Okay, maybe I'll just go through this fairly quickly. The state board is a way of operating the delta. So if you're an engineer trying to operate the delta with pumps, making releases from an upstream reservoir, keeping an eye on water quality, making sure the fish are moving, closing the cross channel, playing around with your barriers in the south delta, adjusting your pumping, you really need to be operating to a set of rules. And so those rules got changed in 1994 and made more stringent. And so what they said is you have to meet a higher water quality. So that ended up costing more water because you had to release more water into the delta or leave more water flowing through the delta to meet those standards. So maybe if you just go to the next one, I'll talk about it as we go. Basically what they said is that we're going to draw some lines in the sand at these 3 points here, and say that historically, if we look at where the salinity had moved into the delta to at certain times historically, we found that the 2 parts per thousand salinity, which remember I said that the ocean was about 35 parts per thousand. So as the Sacramento mixes with the ocean water coming in from this side, you get this gradation of salinity all the way up. And so that historically the 2 parts per thousand has been in this area here for a certain number of days per year in certain months. So what they did is wanted to look at that historically and say, let's set standards that preserve it. So say to the project that you operate your pumps in such a way that in February you meet 2 parts per thousand in some of these locations for 50% of February or 25% of February, depending on other conditions. So those are the rules that are out there. And so what we had to do is come up with rules that were protective for fish and were somehow efficient in terms of trying to not waste water, trying to meet these standards. And so the key there was to understand what had happened historically and again design those standards to work. So we really needed to understand how much flow does it need coming down this river and coming through the San Joaquin part, which is this part here, coming out in this area here. How much delta outflow do you need to meet this particular requirement? And so what we were doing at CCWD was developing a model just of what is the relationship between outflow and salinity. Not only the outflow today, because the outflow today is not what's determining the salinity today. It's an accumulation of what the previous outflows have been. You could have a very high flood that would move all the salt out into San Pablo Bay, for instance, and further out into the bay. And then you could drop the salinity, drop the flow very quickly by turning on the pumps, for instance. And but that salt won't rush back in immediately. It takes a while with the tidal exchange and so on to work back in. So there's not an immediate response to your change in outflow. So what we did is developed an outflow model that was very, very simple. It was just you could do it on a spreadsheet. And what we found is you could model the outflow at Chips Island, which was the middle of those 3 compliance locations, fairly well, something like this. And so what we were able to do then is go through and do the modeling, saying, let's run the historic flows through and see how many days were met under certain conditions within the period that they were interested in, and craft standards that could be then used to operate the delta in the future. So maybe just if you, sorry, maybe page up. One thing though is interesting, that the model is not working, you think, here, but you can see that it is fluctuating a lot about the line as it goes through. So maybe, sorry, if you go to the next one now. And the reason for that, and it is an important part of the delta, just to get into another engineering aspect, and I should be finished in a couple of minutes, is when you talk about the outflow from the delta, usually what you do is you calculate what the flow is at Sacramento, for instance, and what the outflow is coming into the delta from the San Joaquin River, and then usually you just forget about what's happening in the delta. You just say that the water goes through the delta, some of it maybe is exported out, some of it's evaporated or used on the islands, but what they usually forget is the storage in the delta itself. And what happens is that if you look at the tides and you just filter that tide, the storage in the delta is going up and down maybe on a 14-day cycle, and it's not a very regular 14-day cycle, but it is going up and down. And what you find is if you look at the water level in the delta being this full, and you drop it by, what is that, about 1.5 to 2 feet, that's a lot of surface area that you're dropping. And so that's a lot of water that gets squeezed out of the delta into the bay, in addition to any flow coming from Sacramento. And it ends up being a huge amount. And so maybe if you go to the next slide, this just explains it. So you have a model that you put in the calculated outflow that ignores storage in the delta, and then you correct for this raising and lowering of the mean sea level in the delta over a 14-day cycle, and then you put it in your model and see what happens. And then when you do that, you get this sort of fluctuation going on here. And again, we're a little high here and various things, but for instance, look in this region here. What was amazing is when we first did this, we had used another computer model, a more sophisticated computer model, to work out what coefficient we should use to convert change in tidal height times some factor gives you the outflow. And that factor should be related, of course, to the surface area of all the channels in the delta, but we didn't go and measure those. We just looked at what another computer model would give us, and we put it into a spreadsheet, and we ended up picking out, you can see here that this is pretty close to the change that you are getting. And then the driving force here, the rate of change of the mean storage level in the delta, was actually from measured data. So we put that in again, is what the change in water level at a representative location in the delta was. And then created this. So it's a fun model that we use, and it's been very effective for putting into other computer models for quickly calculating how much flow is needed to meet the delta. Okay, and that's the end of my talk. Is that I just put these up as there's a lot of material I used there I put into my slides, or I got my slides from. So if you are interested in following what is this cow-fed thing that he was talking about, there's a lot of information there, almost too much information. And then the California Department of Water Resources does a lot of work on the delta, and they have modeling results, all sorts of modeling results there, and you can actually even run some of their models and see the data plotted out as you get into some of their areas there. And then if you want to go and see what a wonderful water district I worked for, thank you.
We have a few minutes. If there's any questions that anybody would like to ask? Yes.
I'm just curious, what about climate change and the impacts that might be happening with raised sea levels and changed precipitation patterns on the way the delta works?
No, that's a very good point. And it came up in a meeting we were at the other day, where we talk about the common delta pool. Everyone should be in the delta, and everyone should be concerned about the delta, have a stake in the delta. But not only are the levees unstable, but well, if their levees are unstable, they sure as heck are going to be more unstable if there is a sea level rise. And so there is an issue of that. And at one stage, the Natural Heritage Institute threw out a proposal that the Delta farmers didn't think was a great idea. They were saying that if you think about it from that point of view, that there is going to possibly be global warming, sea level rise over the next maybe 100 years, not the next 50 years or the next 10 years. Maybe all those levees go eventually, and the delta is going to be inundated. And so they were saying, well, let's start now. Let's start taking out a lot of those islands and start preparing for it, so we can design a system that works with inundated islands. So they were taking that inundated island one that I showed there and being a little bit more radical. And so it is a real problem. We can never, the levees are already built up enough, and with the peat soil of the delta, all the islands are sinking or blowing away. So you're getting a real mismatch from the geotechnical point of view.
There was the National Research Council in Washington. About 10 years ago, there was a big study on sea level change, relative, because subsidence, sea level, and one of the things they looked at was part of the delta system here in California. But there's places you can go to get a fair idea, because remember, whether something's subsiding or sea level's going up, and you can learn a lot by looking at places that have subsidence. Was there another question up there?
Oh, what did I just point on that, sorry. Is that on global warming, is the other problem with global warming is that the way California water works is that most of your storage, or a lot of your storage, is in a snowpack up in the mountains. So everything is designed, we have our reservoirs that sort of move water out, and then we get the runoff from the snow melt and so on. So with global warming, the snow moves further up and there's less of it, so you've got less storage. That's right. Just some of them.
What's the, you mentioned like the risk of like earthquake associated with levees, and what's the contingency for CCWD kind of water?
Yeah, I focused a lot on the water quality there, but in fact when we were designing the reservoir, part of it is it's a 100,000 acre foot reservoir, but in a sense we only used the top 30,000 acre foot for blending and water quality, and the rest is there, unless it's a really dry year and we get desperate for water quality, is sitting there as in case there is an outage in the delta, we have to go offline for a period of time. And so we designed it that we would impose essentially 25% rationing, and we could survive 3 months off that. And I guess if it was a catastrophic failure in the delta, we'd need longer than 3 months, but that would be a good start. And Metropolitan Water District has built an 800,000 acre foot reservoir, so ours is just 100. So they're at 800,000 acre foot for exactly that kind of purpose, that they can store delta water down there. And if the pumps get shut down for failure in the delta or fish shutdowns, then they're in good shape. So they have a couple of years, I think, is what they're talking. Roberta?
When they were looking at the old river barriers, there was this big discussion over on the San Joaquin whether they should be permanent or temporary. Was there a pro or a con for that? They finally agreed on permanent, but right. It sounded like temporary would be a better way to go.
Well, I think I think there's a problem with permanence that makes people nervous. But I think with the operable barriers, which they were just going to design them essentially as radial gates. Oh. And so if you had your hand on the controls, then you would say, okay, raise it, lower it, and things. It's just, so I think it's much more sensible. Where things are broken down is everyone, I think, all sides of these political arguments agreed that you need to have a head of old river barrier at certain times of year when the fish are moving through the San Joaquin River, either going up or coming back down. You need to cut that off. So at the moment they have temporary barriers, which really is just a pile of rock, which they keep beside the bank. When it's time to put it in, they place them all. And what they find is that they really can't allow a flow down the San Joaquin more than about 5,000 CFS, or those rocks cause flooding of the farms in that area. So the levees start overtopping. The big problem with that is that they're, in trying to come up with standards to operate the San Joaquin River, there's a big program going on, a 10 or 11 year program, where they have design flows being released down the San Joaquin River, which go as high as 7,000 acre-feet. So the whole idea of that was to have higher flows for about a month, move the fish down, put a barrier in, move them by, but there's sort of a disconnect now because you have 7,000 flow coming down past a barrier that can only withstand 5,000. So you really need some sort of movable gate so you can compensate for it. Yeah.
I had a question about the big picture and the problem of designing a sort of compromised, pragmatic solution, because inevitably what happens is we end up with more structures to the river. It's sort of engineering job creation, you know, you try to act within the existing controls, and therefore you add more controls in, you end up with an increasingly dependent system.
Or you move the problem to somewhere else.
Yeah, I mean, through any of this process, has there ever been a notion of a sort of clean slate? So you take away the historical legacy of what's been done, look at what would be the ultimate solution under the contemporary management objectives, and then try and move your solutions, the controls we have now, towards that.
Maybe the British I think the example I showed up there where CalFed is at the moment, that I think if anything they were sort of heading in that direction, because if you'd let us water users or the engineers decide, then we would have ended up with a chain of lakes that would have cost a fortune and it wouldn't have worked and so on, but we would have built it. But I think what they did there, that ended up, the solution they've come up with is just a little bit of tinkering with the delta, keep moving the water through the delta rather than taking it out and creating problems of taking it out through an isolated facility. I mean, that's about as hands-off as we were able to get, I guess, or people were able to get. But it is something that people need to think about, is how else would you have done it, or how should Professor Weigel talked about this idea of putting a barrier in it at the Vallejo Bridge, something like that, and that people may have thought of that as a good idea as well, but one reason that wouldn't have worked is just water quality. That there's so many industries on the upstream side of that and so much ag drainage, you just end up with a big sewer on one side and pure salty water on the other. And it would have been a real mess.
I did not suggest.
He wasn't advocating. But now, it's probably going to come back because someone will say, oh, we can generate power.
All right, this may be a really naive question, but have you ever just thought about moving the intake? Where you take the water from and moving it further up the river?
Say for us? Or?
Yeah, for contrasted water.
Right. Yeah, I mean, if you were to take that literally, then you could say, well, why not build the isolated facility? Because that did move the intake further up. But and for a while, I think CalFed got really close to sort of building, say, a 5,000 CFS isolated facilities. Just a much smaller one, and that could maybe take the water to the Bay Area urban agencies and to maybe somehow we'll find a way of getting to Southern California without getting contaminated with ag water. But it's a tough one for our district because we have a lot of people, our customers are watching us because they live in the Delta, they fish in the Delta, they care about the Delta, and so they don't want us to do anything like that. And I made the joke last time I was here, I think, is that I think our water district area, when they voted against the peripheral canal, probably voted 110% against something like that, just to make sure. But it was one of those things where, from a pragmatic point of view, maybe we shouldn't be holding our customers at ransom by saying, you've got to keep drinking water out of Rock Slough because that keeps the Delta healthy, sort of, in terms of fish and recreation and so on. So I think that idea of expanding Los Vaqueros Reservoir, making it larger, and maybe at times when there's a surplus on the McKellamie River or maybe on the Hetch Hetchy system, the Tuolumne River, maybe some of that surplus water could get put into Los Vaqueros, and that would be a way of moving our intake effectively for the Bay Area agencies further upstream.
Well, if not, thanks again, Jeff.